Hi, my name's Brody, and this is the first presentation of the semester for fluids. And in the problem we're given a uniform, steady flow, and at first it's onto a flat plate, so the stagnation point is just here on the plate. But when you introduce a source, the profile of that will now look like this, and the stagnation point will be raised, and the flow will look more like this. So this bump here is going to have a height of h, and in this problem we're given the stream function of the steady constant flow is equal to axy. And what we're going to try to do in this problem is relate this constant a to this height h and the strength of the source. Oops, I can't spell. Which will be given m. And so, like I said, this is a given stream function for the steady flow, and we know that a stream function for a source is equal to m theta over 2 pi. And what we're going to want to do is superpose these two to get an equation that we can start working with to make the relationships. But first, what we have to do is actually convert this to cylindrical coordinates so we can work with them. And that means the x is going to equal to r cosine theta, and the y is going to be equal to r sine theta. So that will give us the formula psi equals ar cosine theta r sine theta. Jeez. And like I said, we're going to superpose the two. So our overall stream function is then going to be ar cosine theta sine theta plus m theta over 2 pi. And that'll simplify down through some basic algebra and some basic trig identities to a over 2 r squared sine 2 theta plus m theta over 2 pi. So all that really simplifies is this portion here. But we know at this particular situation, our coordinates are standard xy. But we know that the x is equal to 0 and the y is equal to h, the height of this bump, because it's this stagnation point is on the y-axis and just raised. But as that converts to cylindrical coordinates, we know that the theta will equal 90 degrees because this angle here, and r will now equal to h, this height. And I don't know if I explained it before, I meant to, but the stagnation point, all that is where there's no flow. Like it's a stopping point. So like it's where the particles are hitting each other and not flowing there, but everything else is flowing around them. So it's just a stagnant part, and that's why it's called a stagnation point. So that means we'll know that the relative velocity will equal 0 at the stagnation point. And we also know that the relative velocity is equal to 1 over r times d psi d theta, the derivative of the stream function with respect to theta. So once we do that, it'll look like this. Oops. Of this stream function we got here. once we take that derivative, we'll get over AR squared cosine 2 theta plus m over 2 pi. And that's what's going to equal our relative velocity. And like I said, we know relative velocity equals 0 at the stagnation point. So as we continue here, the tangential velocity will also equal 0, but we're just going to keep working with the relative velocity because you can do the same here. It'll give you a different, same end result, different way to get there, because this velocity is also 0, but we're just going to keep working with this one. So then once you have this equation, which will simplify to AR cosine 2 theta plus m over 2 pi r equals 0. Basically, all we're going to do is plug in these here. So I'll write that down again. So we're subbing in theta equals 90 degrees and r equals h. So then once you sub in, we're getting AH cosine 2 90 degrees plus m over 2 pi h equals 0. And this will simplify. Cosine 2 90 is only -1, so negative AH plus m over 2 pi h equals 0. And then basically this is the formula, right? So all we're going to do is take some simple algebra, arithmetic skills and simplify it down, and it will give us that relationship. So this will simplify to AH equals m over 2 pi h. AH equals m over 2 pi. Oh, I just wrote that, duh. H squared equals and then simple square root. H is equal to the square root of m over 2 pi a. And that is our relationship. So that height is the height of this bump here. And depending on the strength of the source, this constant in the stream function, that height will change, because obviously if it's, a stronger flow here or a stronger source, the stagnation point will move up or down. And like I said before, if you don't have that source there, it's basically just running into a wall, right? So the stagnation point's 0 here. And that's it. Here's my signature. That's the first one. Thank you.